Here we're going to be looking at the dilution of solutions, or simply just watering them down. And so we go from something that is concentrate, or at least has a high concentration. Concentrate technically means that it's got as much as possible dissolved in there, but we go from something that's concentrate with a high concentration to something that is a low concentration, simply by adding more of the solvent. They give here the example of watering down orange juice. I gave an example in the past where a student had tried to make Kool-Aid and had done it backwards, using way more of the mix than of the water, and had a really concentrate solution. And so they ended up taking what was supposed to be like 1 gallon of Kool-Aid and made like 20 out of it, or at least could have. I think they just let a lot go to waste. But anyway, getting into this, in dilution, we add more solvent, and so solvent is added, and that increases the volume of the solution, and because of that, then the concentration decreases. But the amount, the mass or moles of solute that is in there remains the same. Now, I don't like this picture that they have here. They have here, this one, if you count it, and we count all these ones that are on the edge as whole particles, they have 22 pieces in there. Well, those 22 pieces are in this tiny volume. Well, over here, we have a much larger volume, just estimating, I'd say that's 4 times. And so then what we need, really, to show this accurately, is instead a box or a circle that is 4 times the size of the original. And then right now, they only have 9 pieces in there. And so we would need the others, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And then these two diagrams actually show what they're talking about up here, that the volume here is tiny and has a certain number of pieces. Here, the volume has increased, but it is the same number of pieces. We are simply changing how much of it is there. There is a way that you can calculate this, and the simple equation is this here. It turns out that if you take a look at the units and you do dimensional analysis, that this is just a fancy way of kind of taking care of the dimensional analysis already. And it's C1V1 equals C2V2. Personally, I will use initial and final a lot of times instead, or before and after. It also turns out you can use this equation for acid-base reactions, and so I frequently use A and B for acid and base as well. I will point out that I was taught M1V1 equals M2V2. I'm going to try to be careful and use the C's here, but I learned it this way because we mostly do in chemistry molarity calculations, since one of the goals here is to give an introduction to the medical sciences. They tend to use quite a few different methods of measuring concentration, as we looked at in prior section, and so just using molarity doesn't make as much sense. But if you see me slip up, that's what I mean there. I will point out as well that when you're doing reactions, you can use this equation, especially in acid base, and a lot of times I'll just put down the individual chemical there. Let's say that we're looking at HCl versus NaOH. I'll just use those as my subscripts instead. But here, where we're dealing with a dilution calculation, where we are starting with one chemical and we have the same chemical the whole time, well, then it doesn't make sense to use the chemical label there. Anyway, getting into doing some practice calculations with these. What is the final concentration? So we want to know concentration final. Oh, when 0.5 liters, that would be volume initial of 6 molar. That is concentration initial. The molar tells me there that that's the concentration. Liters tell me it's a volume. Your units tell you what numbers you're being given. Is diluted to a final volume. So here we have volume final of 1 liter. Well, again, the formula is just C initial times V initial is equal to C final times V final. Course order of operations doesn't matter whether you do the C's or V's first. The concentration to start out with is 6 molar. Multiply that by the 0.5 liter volume that we had to start out with. We want to calculate concentration final, and the volume final, we're told, is 1 liter. Well, you can probably see that if we double the volume, we're going to have the concentration, but mathematically we can work that out. Of course, dividing by 1 liter here on both sides really doesn't change the numbers at all. What it does do, though, is it takes care of canceling out our units. If the liters there cancels with the liters there, and we're left with molarity, which is what we expect for a calculation like this. And so when we do that multiplication, yes, we end up with 3.0 molar is equal to the concentration final of the hydrochloric acid solution. Same thing works out here when we have a mass volume percentage. So this one here, what volume? So we want to know volume final of a 2% mass volume. So that is our concentration reading ahead final. Can be prepared by diluting 25 milliliters. That's going to be volume initial of 14%. That's going to be concentration initial. And so again, CI times VI is equal to CF times VF. Concentration initial is the 14%. Multiply that by the initial volume of 25 milliliters is equal to the concentration final. We are given that this time and asked to solve instead for the volume this time. And we're just going to leave that as a variable. And so then to get the volume final alone, we divide both sides by 2%. The percent is technically not a unit, but it takes the place of a unit here. And then we end up with the 14 times 25 divided by 2, which results in 175 milliliters of solution. I've mentioned it way before, but just to, as a friendly reminder here, one trick that may be tossed out sometimes is to give you one volume in milliliters and ask for the other volume in liters, or to have your concentration units be different. These are both percent mass volume measurements, so they're the same, but you have to make sure you are in the same units, which is part of why I keep my units with me as I'm doing calculations here, trying to make sure that things cancel out properly. Next we have what is the percent, so that's going to be concentration final of solution can be prepared by diluting 10 milliliters. That's volume initial, concentration initial, 9% of 60 milliliters. That's volume final. So once again, the formula, plugging in our numbers then, 9% times 10 milliliters is equal to concentration final is what we're solving for, times 60 milliliters. Divide both sides by 60 milliliters. And we end up with the concentration final equaling 1.5% mass volume NaOH solution. Last practice one here then, what is the molarity of a solution prepared? So that's the N molarity final by diluting that's a volume initial, a molarity initial, and a volume final. There. Now you'll notice already I've slipped back into that MV, but of course M initial is the same thing as C initial in this case, but we'll go ahead and work it out the way that I'm used to just for old time's sake for me. So MV equals MV, and then we have 0.6 molar times by 0.18 liters is equal to molarity final, which is what we're solving for, times by 0.54 liters. Divide both sides by 0.54 liters. And our liters units cancel out. The 0.54 cancels out, and we're left with molarity final is equal to 0.200 molar HNO3 solution. And that finishes up section 5.